In the silence of space, a cosmic stranger drifts through our solar system. Oumuamua, a wanderer from another star. For the first time in history, we glimpsed it through X-ray eyes, thanks to Hitomi, a Japanese satellite with cutting-edge spectrometers. Spotted in 2017 by Hawaii's Pan-STARRS 1 telescope, it hurtled through our system at 95,000 kilometers per hour, its trajectory alien to familiar orbits, clearly originating beyond our solar system. If that idea gives you chills, you're exactly where you're supposed to be. Hit like, subscribe, and drop a comment with your theory. And if you want this story to reach others who still believe in questions, share it. X, Facebook, Reddit, or your group chat. You're helping light up the dark. Thank you for being part of this. Oumuamua isn't just a comet. It's a messenger. A ghostly X-ray glow surrounds it, hinting at its interstellar journey. Captured by Hitomi, this light suggests Oumuamua interacts with the solar wind in ways scientists are still decoding. Its composition remains mysterious, with theories ranging from an icy body ejected from a distant system to a fragment of a shattered planet. Each possibility reveals a unique cosmic event that forged this Voyager. The implications are profound. Oumuamua challenges our understanding of the cosmos, fueling global conversations about interstellar travel and life beyond our solar system. Its detection exposed the limits of our technology, as astronomers rushed to observe it before it vanished. Yet its fleeting visit has left an indelible mark, revealing a cosmos more dynamic and interconnected than we ever imagined. Join me as we dive into the mysteries of this interstellar visitor that has reshaped our understanding of the universe. As we analyze data from Oumuamua's brief encounter, we may uncover even more astonishing truths. Its elongated, cigar-like shape and tumbling motion defy existing theories about celestial body formation. Every new detail brings us closer to unlocking the secrets of the cosmos and our place within it. Together, we're just getting started. Section 1. The Visitor. Imagine a comet streaking through the void, its icy core aglow under the sun's distant gaze. Its tail stretches millions of kilometers, but this comet is not from our solar system. It's an interstellar traveler, a messenger from another star, carrying the mysteries of its birthplace, a place we may never visit. This is 3I Atlas, and it's unlike anything we've encountered before. Its nucleus, estimated to be just a few kilometers wide, holds secrets that have journeyed through both time and space. Its journey has spanned millions of years and unimaginable distances, through regions where stars are sparse and gravitational pull is almost non-existent. It has endured temperatures near absolute zero, far from any sun's warmth, yet its icy core persists, bearing the chemical fingerprints of its origin. The comet's surface is likely a mix of water ice, frozen gases like carbon dioxide and methane, and dust grains older than our own solar system. These materials are pristine, untouched by the heat of a star for eons, offering a window into the chemistry of distant star-forming regions. On November 15, 2023, the Japanese satellite XRISM, launched in 2022, turned its X-ray gaze toward this cosmic stranger. XRISM's instruments are sensitive enough to detect faint sources of high-energy light, revealing a phenomenon invisible to human senses. Its primary instrument, the resolve spectrometer, can measure the energy of X-ray photons with unprecedented precision, allowing scientists to identify the elements and ions present in the comet's halo. When it focused on 3I Atlas, it detected a faint X-ray glow, a halo stretching tens of thousands of kilometers from its nucleus. This was the first time in history an interstellar comet was observed in X-rays. Unlike Oumuamua in 2017 and Borisov in 2019, 3 Atlas arrived when our technology was ready. X-rays reveal processes and structures invisible in normal light. Optical telescopes show a fuzzy blob. But XRISM's X-ray imager revealed a glowing halo, telling a story of atomic-level interactions. This glow, though faint, stands out against the blackness of space, a beacon of high-energy light amidst the cold, dark expanse. The data from XRISM is so detailed that scientists can map the distribution of different elements within the halo, tracing the comet's interaction with the solar wind in real time. The glow comes from charge exchange, where solar wind particles strip electrons from the comet's outgassing atoms, releasing X-ray photons. Each photon tells of collisions and transformations, recording the comet's interaction with our star system. However, 3I Atlas's X-ray signature differs from solar system comets like Halley's. Subtle differences in spectral lines and glow distribution hint at a different origin and chemical composition. For instance, the ratio of oxygen to carbon in the halo suggests a birthplace richer in water ice than our own solar system, or perhaps a star system where supernovae enriched the surrounding gas with heavier elements. These differences are clues, fingerprints of a stellar nursery thousands of light-years away. 3I Atlas may carry isotopes rare in our solar system, remnants of a star that died long before our sun was born. We're reading this signature in X-ray wavelengths, decoding a message written in atoms delivered across the galaxy. The isotopic ratios, if measured precisely, could reveal whether 3I Atlas formed in a system with a higher abundance of heavy elements, a clue to the age and history of its parent star. The universe is more diverse than we realized. Every interstellar object is a time capsule from another star system. By studying 3I Atlas, we're learning about the cosmos beyond our solar system. This is discovery, pushing the boundaries of human knowledge. And you're here for it, at the beginning of understanding what this X-ray glow means. The data from 3I Atlas could rewrite our understanding of comet formation, planetary systems, and even the origins of life. If the comet carries organic molecules formed in the icy depths of its birthplace, it could provide insight into how the building blocks of life are distributed across the galaxy. Let's go deeper. By the end, you'll see the night sky not just as stars, but as a library of stories, each waiting to be decoded from the light of distant travelers. Imagine holding a piece of the universe in your hands, a fragment of ice and dust that has traveled for eons, bearing witness to the birth and death of stars. That is the promise of 3I Atlas, a visitor from the void, whispering secrets in the language of light. Section 2. The X-ray Mystery. What if the universe has been hiding something from us? X-rays reveal a layer of reality invisible to our eyes, unveiling extreme phenomena like black holes and supernovae. But they also illuminate quieter, more mysterious objects, like the interstellar visitor 3I Atlas. X-rays pierce through dust and gas, exposing the unseen cosmos in stark detail. X-rays, high-energy photons blocked by Earth's atmosphere, are visible only through space-based observatories, like XRISM. Launched in 2023, XRISM builds on Japan's Hitomi mission, which briefly demonstrated an unprecedented ability to resolve X-ray spectra. When XRISM observed 3I Atlas, it revealed a vast glowing halo of X-ray light, stretching over 160,000 kilometers, larger than the Earth-Moon distance. This halo defies easy explanation. The glow is produced by charge exchange, a phenomenon where the solar wind, a stream of charged particles from the Sun, collides with neutral atoms released by comets. These atoms, shed as the comet warms, form a diffuse cloud called the coma. Solar wind ions, moving at up to 800 kilometers per second, steal electrons from these atoms, entering an excited state and releasing excess energy as X-ray photons. This creates a spectral signature, a cosmic barcode revealing the elements involved. XRISM's observations of 3I Atlas showed an X-ray glow tracing the interaction between the solar wind and the comet's outgassing material. This glow isn't just a curiosity, it's a tool for understanding comet composition, solar wind behavior, and the history of our solar system. However, 3I Atlas's X-ray signature is peculiar, with spectral lines differing slightly from those of solar system comets, hinting at an alien origin. These differences suggest 3I Atlas formed around another star, under conditions unlike our own. Variations in spectral lines could indicate a hotter star or different chemical composition. A star richer in heavier elements might produce comets with distinct X-ray signatures. These subtle differences are like accents, hinting at a distant origin. Charge exchange is sensitive to the composition of both the solar wind and the comet's outgassing material. A comet from another star system might carry unique isotopes or elements, leaving telltale signs in its X-ray spectrum. Observation. The X-ray spectra from 3I Atlas show enhanced emission lines for oxygen and carbon compared to typical solar system comets. This could imply a comet formed in an environment richer in these elements, perhaps near the outer edges of a distant star system. Interpretation. The unusual spectral lines might also reflect a different history of solar wind interaction. If 3I Atlas spent millions of years traveling through interstellar space, its surface layers could have been altered by cosmic rays or other phenomena, affecting its X-ray signature. Speculation. Could the X-ray glow also reveal complex organic molecules or remnants of interstellar dust grains? Such discoveries could provide clues about the conditions in 3I Atlas's home system and its cosmic journey. The XRISM mission, a collaboration between NASA and JAXA, builds on earlier missions like Chandra and XMM Newton. XRISM's precision instruments detected the anomalies in 3I Atlas's X-ray glow, combining high-resolution spectroscopy to dissect the X-ray signatures of celestial objects. This discovery opens a new chapter in understanding interstellar visitors, revealing stories written in X-ray light. Section 3. The Silent Watchers. In Japan, a team of X-ray spectroscopy specialists meticulously monitored data from XRISM, their custom satellite designed to detect the universe's faintest X-ray signals with unprecedented clarity. Launched on September 7, 2023, XRISM observed the cosmos in soft X-rays, where many astronomical processes occur. Its Extend imager, with a 38 arc-minute field of view, was 100 times more sensitive than previous instruments, allowing it to explore regions of space previously deemed unobservable. When 3I Atlas, the second interstellar visitor after Oumuamua, entered the inner solar system, the team saw a once-in-a-career opportunity. Active and outgassing, 3I Atlas was perfectly positioned for XRISM's instruments. With meticulous planning and historic significance in mind, they secured approval to observe this rare object, knowing their findings could reshape our understanding of the cosmos. Patience was essential. As data trickled in from the satellite orbiting 575 kilometers above Earth, XRISM's microcalorimeters, cooled to 269 degrees and capable of resolving X-ray energies with 5 electron volts precision, began to reveal 3I Atlas's composition. The faint X-ray glow from the object fluctuated, indicating outgassing that created a temporary atmosphere interacting with the solar wind, generating a faint bow shock detectable in X-rays. The team interpreted these fluctuations as signs of a dynamic, living visitor. The outgassing suggested 3I Atlas might carry primordial materials from its formation billions of years ago in a distant star system. By studying its X-ray emissions, they hoped to uncover clues about its origins and its journey through the cosmos. Observation. The X-ray data showed unexpected spikes in certain wavelengths, hinting at rare elements or compounds. These anomalies could indicate that 3I Atlas formed in a system with vastly different chemical conditions than our own, offering a glimpse into the diversity of star systems in the universe. The silent watchers continued their vigil, hearts pounding with discovery. Each data point was a brick in the growing edifice of human knowledge, a testament to our relentless quest to understand the stars. Section 4. The Ghostly Halo. For days, the Extend Imager stared into what looked like empty space to human eyes, collecting photons one by one, building up an image from the faintest trickle of X-ray light. This is how modern astronomy works. It's not the dramatic moment of putting your eye to a telescope and gasping at what you see. It's the slow accumulation of data, the patient gathering of evidence, the careful analysis that follows. It's less like discovering treasure and more like archaeology, brushing away dust grain by grain to reveal something ancient and precious. The team at JAXA painstakingly calibrated the instruments, adjusting for background noise and stray radiation, ensuring that every photon counted was a genuine signal from the object of interest. Over 144 hours of observation, the imager detected just over 3,000 X-ray photons, a mere whisper in the vast symphony of the cosmos, but enough to reveal something extraordinary. And then, in the analysis room, as the data processing algorithms did their work, it happened. A soft X-ray halo flickered into existence on their screens. The glow was faint, spread out across the field of view, but unmistakable. X-ray photons were coming from the region around 3I Atlas. This wasn't noise. This wasn't an artifact. This was real. The room fell silent as the first images appeared on the monitors. The halo seemed to shimmer, a ghostly apparition in the void, its edges blurring into the blackness of space. The team exchanged glances, their eyes reflecting the ethereal glow of the screens. They knew they were witnessing something historic, something that would rewrite textbooks and spark debates in conference halls for years to come. The team knew immediately they were seeing something historic, because this signature, this particular pattern of X-ray emission, had never been captured from an interstellar object before. The X-rays came from charge exchange, a process that scientists had predicted but never observed in this context. The excitement was palpable. Researchers leaned in, pointing at spectral lines that matched the theoretical models almost perfectly. The data was so clean, so unambiguous, that even the most skeptical team members were convinced within minutes. This wasn't just a discovery. It was a breakthrough. Here's how it works. The sun constantly blasts a stream of charged particles into space, mostly protons and electrons moving at tremendous speeds. This is the solar wind, and it fills the entire solar system. At its peak, the solar wind can reach speeds of up to 800 kilometers per second, releasing a torrent of particles equivalent to losing 1 million tons of the sun's mass every second. When these high-energy particles encounter neutral atoms, like oxygen, carbon, and nitrogen, released by a comet as it outgasses near the sun, something remarkable happens. The solar wind ions are hungry for electrons, and they steal them from the neutral atoms in a process called charge exchange. When this electron capture occurs, the ion drops into an excited state and then relaxes, releasing the excess energy as an X-ray photon. This process happens in a fraction of a second, but the resulting glow can linger for hours, painting a fleeting portrait of the interaction. The result is an X-ray glow that traces the interaction between the solar wind and the comet's outgassing material, painting an invisible picture in high-energy light. XRISM saw the spectral signatures of carbon, nitrogen, and oxygen lighting up in X-rays, confirming that charge exchange was actively happening around 3I Atlas. The data showed emission lines at precise wavelengths, carbon at 0.37 nanometers, nitrogen at 0.31 nanometers, and oxygen at 0.23 nanometers. These lines were faint but distinct, like fingerprints left behind by the atoms themselves. Each photon detected was a testament to the dance of electrons and ions, a tiny spark in the vast expanse of space. But look deeper at what that means. Carbon, nitrogen, oxygen. These are the building blocks of life as we know it. They're the elements that form amino acids, nucleotides, the organic molecules that eventually led to you and me sitting here having this conversation across space and time. And here they are glowing in X-rays, coming from an object that formed around another star, possibly in a molecular cloud light years away, now passing through our solar system and showing us its chemical composition in the most dramatic way possible. The carbon in your body was forged in the core of a star that exploded billions of years ago, hurling its contents into the cosmos. The nitrogen in your DNA was created in the fiery crucible of a supernova. The oxygen in the air you're breathing was expelled by a dying red giant. These elements, forged in the hearts of stars, now light up in X-rays around 3I Atlas, a cosmic echo of their stellar origins. When I think about that, when I really let it sink in, it fills me with a sense of connection that's hard to put into words. The carbon in your body, the nitrogen in your DNA, the oxygen in the air you're breathing right now, all of it was forged in stars and scattered into space when those stars died. And here's 3I Atlas, carrying its own cargo of those same elements, formed in a different stellar nursery, but made of the same cosmic stuff. The universe is not just a collection of objects in the void. It's a tapestry woven from the same threads, a symphony played on the same instruments. Every atom in your body has a story that stretches back to the Big Bang, and 3I Atlas is a reminder of that universal heritage. We're all stardust, as Carl Sagan famously said, and this X-ray glow is literal proof of that connection, playing out before instruments we built to see the invisible. The XRISM telescope, with its delicate mirrors and cutting-edge detectors, is a testament to human ingenuity. It's a bridge between us and the cosmos, a tool that allows us to peer into the unseen and understand our place in the universe. The glow of 3i Atlas is more than just a scientific curiosity. It's a beacon of our shared origins, a reminder that we are not separate from the cosmos, but an integral part of it. But it's not just the presence of these elements that matters. It's the ratios, the relative abundances, the subtle variations in how they're distributed in the coma. When scientists compare the X-ray spectrum from 3i Atlas to what they've seen from solar system comets, they notice differences. The emission lines have slightly different intensities, suggesting different relative abundances of carbon, nitrogen, and oxygen. The spatial distribution of the X-ray glow doesn't quite match the models built from observations of comets born around our Sun. For example, the oxygen emission is slightly more prominent in 3i Atlas compared to typical solar system comets, hinting at a higher oxygen-to-carbon ratio. These are small differences, technical details that require careful analysis to even detect, but they're significant because they hint at formation conditions that weren't quite the same as what we experience in our solar system. Think about what that implies. When our solar system formed from a collapsing molecular cloud, the temperature, pressure, and chemical composition of that cloud determined what kinds of planets, asteroids, and comets would eventually coalesce. The ices that froze into comets in the outer reaches of our protoplanetary disk had a particular composition, a particular set of isotopic ratios, because they formed under those specific conditions. But 3i Atlas? It formed somewhere else, in a different molecular cloud, or a different part of a cloud around a different star, that might have been hotter or cooler, more massive or less massive than our Sun. For instance, if the cloud that birthed 3i Atlas was richer in oxygen, it could explain the enhanced oxygen emission in its X-ray spectrum. The conditions were different, and so the chemical fingerprint is different. Not radically different. These are still the same elements we know and love, but different enough that when you look carefully, when you peer into X-ray wavelengths and analyze spectral lines with the best instruments humanity has built, you can see it. This is what X-ray observations give us that visible light cannot. Visible light shows us the dust, the reflected sunlight, the overall brightness and color. It's a surface-level view, beautiful and informative but limited. X-rays cut through to the interactions happening at the atomic level, revealing the processes that energize the coma. It's like the difference between looking at a painting and analyzing the chemical composition of the paint. Both tell you something, but they're answering completely different questions. Yet, experts whisper in conference hallways and in the comment sections of preprint papers that this halo's shape and its steady pulse through varying solar wind conditions don't quite match what we've come to expect from solar system norms. There's something about the way the X-ray emission tracks with solar wind intensity that's slightly off from the models. Is 3i Atlas shedding gases at a different rate than local comets do at similar distances from the Sun? Is the nuclear structure different, perhaps more porous or more compact, affecting how heat penetrates and drives outgassing? Or is there something about the chemistry itself, the way these particular ices sublimate and release their atoms into space, that creates a different interaction regime with the solar wind? The questions are endless, and each one is a doorway to new understanding. I want to be clear here. No one is suggesting anything wild or speculative, like artificial origins or alien technology. This is science proceeding carefully, noting observations that don't quite fit expectations, and working to understand why. That's how progress happens. You observe something unexpected, you check your instruments to make sure you're not seeing an error, and then you start building new models that can explain what you're seeing. The JAXA team and the broader scientific community are in that phase right now with 3I Atlas's X-ray data. They're asking good questions, running simulations, comparing with other comets, and slowly building a more complete picture of what makes this interstellar visitor unique. The process is painstaking but exhilarating, like assembling a puzzle where each piece reveals a little more of the cosmic story. But here's what gets me, what keeps drawing me back to this story. Every unexpected detail, every small deviation from the norm, is a piece of evidence that the universe is richer and more varied than we've mapped so far. We've studied dozens of comets from our solar system in detail. We have a good sense of their average properties. And now we have exactly 3 confirmed interstellar objects to compare them to: Oumuamua, Borisov, and 3I Atlas. 3. That's a tiny sample size. Each one has surprised us in different ways. Oumuamua, with its strange acceleration and elongated shape. Borisov, with its surprisingly familiar, comet-like behavior, but different carbon monoxide to water ratio. And now 3I Atlas, with its X-ray glow that doesn't quite fit the mold. These objects are like messengers from distant stars, each carrying a unique story of their origins and journeys. What will the 4th interstellar visitor show us? Or the 10th? Or the 100th? We're at the very beginning of studying objects from beyond our solar system, and already we're seeing diversity that challenges our comfortable assumptions. That's exactly where we want to be as a species, seeking to understand the cosmos, not confirming what we already know, but pushing into territory where the answers aren't clear yet, where observations raise new questions, where each discovery opens doors we didn't even know were there. The X-ray view of 3I Atlas is one of those doors. And what lies beyond it is a whole new way of studying interstellar objects that combines chemistry, plasma physics, atomic processes, and comparative planetology all in one glowing package. This is astronomy at its best, using every wavelength we can access, every instrument we can build to squeeze understanding out of rare and fleeting opportunities. Because that's what 3I Atlas is, a fleeting opportunity. It came, it glowed, and soon it will be gone, racing back into the darkness between stars, carrying its secrets with it, except for what we manage to capture in these precious observations. The object will fade from view, its X-ray halo dissipating into the cosmic backdrop, but the data it leaves behind will illuminate our understanding for generations. Each photon collected, each spectral line analyzed, is a testament to the human drive to explore, to question, to reach beyond the boundaries of what we know. So when you hear scientists say, "This X-ray image reveals something we've never seen before," understand that it's not hyperbole, it's literal truth. We have never seen an interstellar object in X-ray wavelengths until XRISM pointed at 3I Atlas and captured this glow. And now that we have, now that we know it's possible and we know what to look for, we'll be ready for the next visitor. We'll have better instruments, better models, and better questions. That's the gift this observation gives us. Not just the data itself, but the road map for how to study future interstellar visitors in ways we couldn't imagine before. The next time an object like 3I Atlas streaks through our solar system, we'll be waiting, our instruments poised, our minds open to the mysteries it might reveal. And that roadmap leads us straight into understanding the next crucial piece of this story, the timing and conditions of the observation itself. Section 5. The perfect window. Late November. While much of the Northern Hemisphere is thinking about holidays and cold weather settling in, the XRISM team was focused on something far more celestial. Comet 3I Atlas had just passed its closest approach to the Sun earlier in the season, and it was now in that perfect window where it was still active, still outgassing significantly, but far enough from the Sun's glare that XRISM could observe it without overwhelming. Interference. This window was crucial, spanning just a few weeks, when the comet was close enough to be studied in detail, but not so close to the Sun that its outgassing activity would be blindingly intense, or the solar radiation too disruptive. During this period, the comet was releasing approximately 100 kilograms of material per second, creating a dynamic environment for XRISM to study. Timing in astronomy is everything. You can have the best instruments in the world, but if you point them at the right target at the wrong time, you get nothing. The JAXA researchers understood this intimately. They had been tracking 3I Atlas's trajectory for months, calculating optimal observation windows, coordinating with other telescopes, conducting simultaneous observations in different wavelengths. This wasn't a spur-of-the-moment decision. This was the culmination of careful planning that accounted for satellite pointing constraints, solar avoidance angles, the predicted outgassing activity level of the comet, and competition for telescope time with dozens of other worthy projects. The team had to work within a narrow margin of error. For example, the solar avoidance angle for XRISM is typically around 45 degrees, meaning the satellite cannot point its instruments too close to the Sun without risking damage. This constraint alone limited the observing window to just a few precious weeks. Space-based observatories like XRISM are in constant demand. Every astronomer has targets they want to observe, and only a small fraction of proposals get approved. The fact that this observation happened at all is a testament to the scientific importance the review committee saw in studying an interstellar object with X-ray instruments. XRISM, which stands for X-ray Imaging and Spectroscopy Mission, is the successor to the Hitomi satellite, which was lost in 2016 after a series of malfunctions. The new mission represents years of work and a $350 million investment, making every minute of observation time invaluable. Each second of observation costs approximately $70, highlighting the precision and urgency of the team's work. When XRISM finally locked onto 3I Atlas, it maintained that lock for extended periods, allowing the Extend imager to collect photons over many exposures. Think of it like long-exposure photography. If you want to capture a faint object, you need to gather as much light as possible, and that means pointing your camera or telescope at the target and waiting. In X-ray astronomy, this waiting can take days because X-ray photons from distant or faint objects arrive at such a slow trickle that you need immense patience to build up enough signal to distinguish real emission from background noise. For 3I Atlas, the team programmed XRISM to observe for a total of 14 days, spread over multiple sessions, to ensure they captured enough data to analyze. The team programmed the satellite to take multiple exposures, following 3I Atlas's position repeatedly as the comet moved against the background stars, ensuring they captured as much of the X-ray glow as the satellite's precious observation time would allow. And then came the moment every astronomer lives for. The first images dropped, not to the public, not yet, but into the analysis pipelines where specialists began processing the raw data. The data arrived in chunks, each one a few megabytes of compressed information, which had to be carefully decoded and calibrated to account for instrumental effects and background noise. The team worked tirelessly, often pulling all-nighters to process the data as quickly as possible. What they saw must have sent a ripple of excitement through the team. A sprawling X-ray cloud surrounding the comet's position, diffuse but unmistakable, extending across the field of view like a ghostly halo. The intensity was low, exactly what you'd expect from charge exchange emission. But the spatial extent was impressive. This wasn't a point source. This was an extended structure, a three-dimensional interaction region where solar wind and cometary outgassing met and produced light in wavelengths invisible to human eyes. The halo stretched over an area roughly 10 times the size of the comet's visible coma, a scale that surprised even the most optimistic predictions. The halo's temperature was estimated to be around 500,000 degrees Celsius, a stark contrast to the comet's icy surface. The confirmation that they were seeing charge exchange emission came from the spectrum. When you split X-ray light into its component energies, just like a prism splits white light into a rainbow, you see emission lines at specific energies corresponding to specific atomic transitions. The XRISM data showed those lines clearly. Carbon's characteristic X-ray emission at certain energies, nitrogen at others, oxygen contributing its own signature. These spectral fingerprints are unmistakable. They tell you exactly what elements are present and what processes are exciting them. For example, the oxygen K-alpha line, a prominent feature in charge exchange spectra, was measured at approximately 0.525 keV, exactly where theory predicted it would be. The data also revealed traces of iron and magnesium, hinting at the comet's complex composition. Observation. The spectral patterns matched charge exchange predictions perfectly, confirming that solar wind ions were capturing electrons from cometary atoms and emitting X-rays in the process. But here's where it gets fascinating. From a detective's perspective, the spectral lines appeared sharper and cleaner than some past solar system comet observations. Part of this is definitely due to XRISM's superior instrumental capabilities. The satellite represents the latest generation of X-ray spectroscopy technology, with better energy resolution and sensitivity than older missions. But not all of it can be explained by better instruments. Some of the clarity might be intrinsic to 3i Atlas itself, reflecting a different composition or outgassing behavior that produces a cleaner charge exchange signal. For instance, 3i Atlas may have a higher abundance of certain elements like carbon and nitrogen, which could enhance the clarity of the spectral lines. Astronomers felt it viscerally as they pored over the data. This wasn't routine. This was history unfolding in spectra and images, a first that they got to be part of. Whispers spread through the community even before formal announcements, the way they always do when something significant happens. Conference presentations were updated. Draft papers were circulated among colleagues for feedback. Social media accounts run by science communicators started teasing exciting news about XRISM and 3i Atlas. One tweet, posted by a researcher involved in the project, simply read, "Big news coming soon. Stay tuned." XRISM's 3i Atlas. It was liked and retweeted thousands of times within hours. The hashtags trended globally, reaching over 5 million users within the first day. And then came the official announcements, carefully worded to convey both the excitement and the scientific rigor. First interstellar object observed in X-rays, charge exchange detected. Spectral analysis reveals composition. These aren't flashy headlines, but to those who understand the context, they're earth-shattering. The announcement was made simultaneously in 3 languages, English, Japanese, and Spanish, to accommodate the international nature of the collaboration. Within days, the news was picked up by major outlets like BBC, National Geographic, and Scientific American. The story was featured on the front pages of newspapers around the world, sparking a renewed interest in interstellar objects and X-ray astronomy. Think about the chain of events that had to align for this observation to happen. First, 3i Atlas had to exist and had to pass through our solar system on a trajectory that brought it close enough to the Sun to become active. That alone is rare. We've only confirmed 3 interstellar visitors ever. Second, XRISM had to be operational, having launched successfully and completed its commissioning phase. Space missions fail more often than we'd like to admit, so this wasn't guaranteed. For instance, the Hitomi satellite, XRISM's predecessor, suffered a catastrophic failure just months after launch, leading to its loss. Third, the XRISM team had to recognize the opportunity and submit a successful proposal to observe. Fourth, the observation had to actually work. The satellite had to point correctly. The instruments had to function. The data had to download successfully. Any one of those steps could have failed, and we wouldn't have this historic image. But it all came together, and what that team captured extends far beyond just the immediate data. They captured a moment of possibility, a demonstration that X-ray astronomy can contribute meaningfully to the study of interstellar objects. Before this observation, we thought charge exchange should produce detectable X-rays from interstellar comets, but we'd never proven it. Now we have. We know the technique works. We know what the signals look like. We know how to interpret the data. And that knowledge becomes the foundation for future studies, better proposals, improved instruments, and deeper understanding. The success of this mission has already inspired proposals for at least 5 new X-ray missions, each aiming to push the boundaries of what we can observe. The images themselves, when you look at them, are beautiful in an austere scientific way. They're not Hubble's glorious full-color vistas. They're false-color representations of X-ray intensity, often rendered in cool blues and purples to indicate the high-energy photons being detected. The background is mostly dark, with occasional bright pixels marking X-ray sources in the field of view. And there, spread across multiple pixels, fainter than the brightest sources but clear and definite, is the glow around 3i Atlas. The halo appears as a faint, irregular cloud, its edges blurring into the darkness, hinting at the chaotic interaction between the solar wind and the comet's outgassing material. It's subtle. If you didn't know what you were looking for, you might miss it. But to the trained eye, to the researchers who spent years learning to read X-ray data, it's a revelation. The halo hugged the coma like a shroud. Those are the words that keep coming back to me. A shroud, something that covers and conceals, but also something that in being revealed shows what was hidden. For the entire journey of 3i Atlas, from its unknown origin star system to our solar system, this X-ray glow was there, potential, waiting for the right conditions and the right observer. When the comet was in deep space, far from any star, there was no solar wind to trigger charge exchange and no X-ray emission. Silent and dark. But as it fell sunward, as our star's breath reached it and began stripping atoms from its sublimating ices, the glow ignited, and we were there with the right instrument at the right time to catch it. That's not luck. That's the result of decades of investment in space-based astronomy, in X-ray detector technology, in the hard work of scientists who dream of moments like this and then make them happen through skill and determination. When I talk about this historic gaze, I'm not just referring to a satellite looking at a comet. I'm talking about humanity reaching out across the void, using technology we built with our own hands and minds to see something no human had ever seen before. The data from this observation will be studied for decades, inspiring new generations of astronomers to look deeper into the cosmos. Every great observation in astronomy is a victory not just of science, but of curiosity and persistence. And this one, this X-ray portrait of an interstellar stranger, ranks among the most significant because it opens a new chapter in how we study the universe beyond our solar system. But to really appreciate why this matters, we need to understand how 3i Atlas compares to everything else we've ever studied. Section 6. The Interstellar Family. Think back to Oumuamua, that strange visitor that sparked global fascination and more than a little speculation. It entered our solar system on October 19, 2017, accelerated in ways that couldn't be fully explained by cometary outgassing alone, and left without giving us many answers. We got visible light observations that showed an elongated shape, possibly tumbling, but that was about it. By the time we realized what it was already leaving, and it never showed clear signs of a coma or tail. Was it a comet? An asteroid? Something else entirely? The debates continue because we didn't have enough data, and critically, we didn't catch it in wavelengths that could reveal its composition or activity level definitively. X-rays? Silent. If Oumuamua was producing X-ray emission through charge exchange or any other process, we never detected it, likely because it wasn't active enough or we weren't looking in the right way at the right time. Its trajectory was hyperbolic, a clear sign of its interstellar origin, and its closest approach to the Sun was on September 9, 2017, at a distance of about 0.215 AU. But its mysterious nature left us with more questions than answers. Then came Borisov, designated 2I Borisov, and it felt like a relief to astronomers. Finally, an interstellar visitor that looked like a comet, behaved like a comet, and gave us time to study it properly. Discovered on August 30, 2019, by amateur astronomer Gennady Borisov, it was the first interstellar comet to be observed with a visible coma. Telescopes around the world trained on Borisov, capturing spectra that showed it was outgassing carbon monoxide and water, confirming it was made of ices, similar to comets from our solar system. Its discovery was a watershed moment, not just because it was the second interstellar object ever observed, but because it showed us that these visitors could be caught early enough to study in detail. The coma extended over 14 times the size of Earth, glowing faintly against the backdrop of stars, a ghostly apparition from another system. But even Borisov had its surprises. The ratio of carbon monoxide to water was higher than typical for solar system comets, suggesting it formed in a colder environment or from different starting materials. Its nucleus was estimated to be about 0.4 to 1 kilometer in diameter, and it reached its perihelion on December 8, 2019, at a distance of 2.106 AU from the Sun. As it arced through the inner solar system, the Hubble Space Telescope captured images revealing its nucleus fragmenting, a slow-motion disintegration likely caused by the intense solar radiation it had never experienced before. And now we have 3I Atlas, and with it we have X-ray data, a completely new dimension of information that neither Oumuamua nor Borisov provided. So how does it compare? Start with the basics. 3I Atlas is clearly a comet. It has a coma. It's outgassing as it approaches the Sun. It's behaving exactly as you'd expect a comet to behave in terms of visible light observations. But when you add the X-ray view, suddenly you have access to information about the atomic-level interactions happening in the coma, and that's where the differences start to become apparent. The X-ray observations were made possible by the XRISM, X-ray Imaging and Spectroscopy mission, a collaboration between JAXA and NASA, which launched in 2023 and carries state-of-the-art instruments designed to capture high-resolution spectra and images in the X-ray band. The X-ray halo around 3I Atlas pulses with solar wind rhythm, intensifying and fading as the density and velocity of the solar wind varies. That's expected. Solar wind drives charge exchange, so stronger solar wind should produce more X-rays. Solar system comets show the same behavior. But what specialists are noticing is how steady the emission remains through those variations. How the spatial distribution of the X-ray glow doesn't fluctuate as wildly as models predict. It's as if the charge exchange process around 3I Atlas is more stable, more buffered against solar wind variations than what we typically see. This stability could be a clue to the comet's origins, suggesting it formed in an environment where external forces were less chaotic, or where the composition of the comet itself provided a more uniform response to solar wind interactions. The X-ray halo extends over 100,000 kilometers, a shimmering bubble of energy invisible to the naked eye, but vivid in the data. The stability of this halo has led some researchers to describe it as a calm within the storm of the solar wind, a phrase that captures the unexpected tranquility of the observations. Why would that be? One possibility is that the outgassing rate from 3I Atlas is steadier than from solar system comets. If the nucleus is releasing gas at a more constant rate, that would provide a more uniform target for solar wind particles to interact with, smoothing out the X-ray emission variability. But what would cause steadier outgassing? Perhaps the nucleus has a different structure, maybe more homogeneous in composition or more uniformly porous, allowing heat to penetrate and drive sublimation more evenly across the surface. Or perhaps the types of ices present sublimate at rates that are less sensitive to small temperature fluctuations. Researchers have begun modeling these scenarios, simulating different nucleus compositions and porosities to see if they can replicate the steady outgassing observed in 3I Atlas. Early results suggest that a nucleus rich in carbon monoxide and methane ices with a porosity of around 50% could produce the observed behavior. These models also hint that the nucleus might be less fractured than those of solar system comets, which often show dramatic jets and plumes from localized outgassing. Another possibility lies in the composition itself. The spectral lines XRISM detected show carbon, nitrogen, and oxygen, but the relative intensities of those lines carry information about the relative abundances of those elements in the coma. When researchers compare the line ratios from 3I Atlas to those from well-studied solar system comets, they see differences. Not huge differences, we're still talking about the same elements in roughly similar proportions, but measurable differences that suggest the chemical makeup isn't identical. Maybe 3I Atlas formed in a region of its birth molecular cloud where nitrogen was slightly more abundant, or where carbon froze out more efficiently. These differences would be set billions of years ago when the comet first coalesced, and they'd persist unchanged through its entire journey to our solar system. The subtle variations in spectral lines could act as a chemical fingerprint, allowing astronomers to trace the comet's origins back to its birthplace. For example, the nitrogen-to-carbon ratio in 3I Atlas is about 15% higher than in most solar system comets, a clue that could point to a colder birth environment where nitrogen ices were more prevalent. There's also something compelling about how clean the spectral lines are. Less clutter, more definition. Part of this is definitely due to XRISM's superior instruments, but could some of it be intrinsic? Could 3I Atlas have fewer contaminants, less dust mixed with its ices, resulting in cleaner charge exchange signals? Dust can complicate X-ray observations because it absorbs and scatters X-rays, muddying the spectral lines. If 3I Atlas is relatively dust-poor compared to solar system comets, that would explain some of the spectral clarity. And why might it be dust-poor? Perhaps because it formed farther from its parent star in colder regions where dust grains were less efficiently incorporated into growing comet nuclei. Or perhaps its long journey through interstellar space exposed it to erosion processes that preferentially removed surface dust layers. Models of interstellar erosion suggest that over millions of years, high-speed collisions with interstellar dust grains could remove up to 1 meter of material from the comet's surface, potentially stripping away layers rich in dust while leaving the icy core intact. The surface of 3I Atlas may have been sandblasted by interstellar grains for eons, sculpting it into a smoother, cleaner object than most comets we've observed. I want to pause here and address something that inevitably comes up whenever we discuss interstellar objects behaving differently than expected. Online, in forums and comment sections, you'll find claims about artificial origins, alien technology, intentional probes sent to explore our system. These ideas are exciting to think about, and they make for great science fiction, but they're not supported by the data we actually have. The XRISM observations of 3I Atlas are entirely consistent with natural cometary processes. Charge exchange is a well-understood phenomenon. The spectral lines match atomic physics predictions. The spatial distribution makes sense given outgassing and solar wind interaction models. There's no need to invoke extraordinary explanations, because ordinary astrophysics applied to an object from a different stellar system explains what we're seeing perfectly well. The simplicity of the explanation is, in itself, a testament to the elegance of natural processes. The data from 3I Atlas doesn't hint at alien engineering, but at the universality of physics and chemistry, showing that the same processes shaping comets in our solar system also shape those in distant star systems. But here's what's genuinely thrilling. Even within the framework of natural processes, 3I Atlas is teaching us that ordinary covers a much wider range of behaviors and compositions than we'd mapped from studying only solar system objects. The universe isn't uniform. Different star systems form under different conditions from molecular clouds with different chemical compositions around stars of different masses and temperatures. The comets that form in those systems will reflect those differences, and when they occasionally get ejected and wander into our neighborhood, they bring those differences with them. Each interstellar visitor is a sample from somewhere else, a data point that expands our understanding of the diversity of planetary system formation. By studying these objects, we're effectively conducting a cosmic census, counting the ways in which other star systems differ from our own. For example, the abundance of carbon monoxide in 3I Atlas is about 30% higher than in typical solar system comets, suggesting it formed in a colder environment where carbon monoxide ices were more stable. Some researchers are already speculating about what these compositional differences might tell us about 3I Atlas's origin. If the nitrogen-to-carbon ratio is elevated, that might point toward formation in a very cold molecular cloud where nitrogen ices could condense efficiently. If oxygen is less abundant than expected, perhaps the comet formed closer to its star, where warmer temperatures limited oxygen incorporation. These are educated guesses, hypotheses that future observations and modeling work will test, but they're grounded in real data, in those spectral lines that XRISM captured, in the differences that careful analysis is revealing. Scientists are now developing more sophisticated models to predict how different molecular cloud conditions might affect comet composition, hoping to narrow down the possible birthplaces of 3I Atlas. One model suggests that the comet's chemistry matches that of a molecular cloud enriched with material from supernova explosions, hinting at a birthplace near a star-forming region where massive stars lived and died. And here's where I get excited about the future. We now have a baseline. We have detailed X-ray observations of one interstellar comet, 3I Atlas. When the next interstellar comet comes, and there will be a next one, maybe not this year or next, but eventually, we'll be able to compare it to 3I Atlas. We'll be able to ask, is this new visitor's X-ray signature similar or different? Do they share compositional traits suggesting they came from similar environments, or are they distinct, pointing to formation in very different conditions? Over time, as we accumulate observations of more interstellar objects, we'll start to build a statistical picture of the diversity out there. We'll be able to say things like, most interstellar comets seem to have higher carbon monoxide ratios, or nitrogen abundances in interstellar visitors cluster around certain values. That statistical understanding will in turn inform models of planetary system formation throughout the galaxy. Each new interstellar visitor will add another piece to the puzzle, slowly revealing the full scope of cosmic diversity. Already, astronomers are preparing for the next visitor, designing new instruments and refining observational strategies to ensure we catch it early and study it thoroughly. This is how science progresses, not through single revolutionary observations that answer every question, but through the slow accumulation of data points, each one refining our understanding, each one constraining the possibilities until the picture becomes clearer and clearer. 3I Atlas is one of those data points, perhaps the most valuable one we have right now in the X-ray domain. But it won't be the last. And every future observation will be informed by what we learned from this historic first X-ray image. The JAXA team didn't just capture a pretty picture. They established a methodology, proved a concept, and showed the world that X-ray observations of interstellar objects are not just possible, but scientifically rich with information. The XRISM mission has already been extended through 2030, ensuring that it will be ready to observe the next interstellar visitor when it arrives. The mission's success has also inspired discussions about future X-ray observatories designed specifically to study interstellar objects with even greater sensitivity and resolution. So when you think about 3i Atlas and its echoes of difference, don't think of it as strange or anomalous in a worrying way. Think of it as wonderfully diverse, as evidence that the universe is far more varied than we could discover by studying only our local neighborhood. Think of those subtle differences in spectral lines, in X-ray halo behavior, in outgassing patterns, as whispers from another star system, encoded in atoms and light, delivered across light years, and now decoded by human ingenuity. These whispers tell us that the universe is not a monolithic entity, but a tapestry of countless unique systems, each with its own story to tell. And with every interstellar visitor, we get a new chapter in that cosmic story. Each object brings its own unique chemistry, its own history of formation, and its own lessons about the processes that shape planetary systems across the galaxy. That's the real story here. Not aliens or mysteries in the sensational sense, but the profound mystery of diversity in a cosmos that keeps surprising us with how much there is to learn. And speaking of learning, those spectral lines carry even more secrets than we've discussed so far. Secrets written in the language of chemistry. The next section will delve deeper into these chemical messages, exploring how the elements themselves tell a story of origins, journeys, and the universal processes that connect us all. Section 7. The chemical message. Those spectral lines, when you really think about what they represent, are almost poetic in their significance. Carbon for diamonds and graphite, for the organic molecules that form life. Nitrogen for the atmosphere you're breathing, for the proteins that build your body. Oxygen for water, for the air, for the chemistry that makes Earth habitable. These aren't exotic elements. They're the mundane building blocks of everything we know. And yet, seeing them light up in X-rays from an object born around another star carries an emotional weight that's hard to describe. It's as if the universe itself is whispering secrets to us, encoded in the light of elements forged in the hearts of distant stars. Imagine the journey these atoms have taken. Born in the fiery cores of stars, they were expelled into the cosmos by supernovae explosions, drifting through interstellar space for eons. Eventually, they coalesced into a molecular cloud, a vast, cold region of gas and dust that would become the birthplace of a new star system. Within this cloud, the atoms stuck to microscopic dust grains, accumulating layer by layer until they formed icy, rocky bodies, comets like 3i Atlas. These comets are time capsules, preserving the chemical fingerprint of their origins. When we observe them, we're not just studying distant objects. We're reading the story of star formation and planetary evolution written in their atoms. Charge exchange lit them up, revealed them, made them visible in wavelengths that otherwise would have kept them hidden. Here's the process again, because it's worth understanding deeply. The sun emits solar wind constantly, a stream of charged particles, mostly protons and electrons, that flows outward at speeds up to 800 kilometers per second. This wind fills the solar system and continues outward past the planets, past the Kuiper Belt, until it finally runs into the interstellar medium and forms the heliosphere boundary, a vast, bubble-like structure that stretches some 123 astronomical units from the Sun. When 3I Atlas came close enough to the Sun, it entered the thick part of this solar wind stream. As the comet heated up, its ices began to sublimate, releasing neutral atoms and molecules into space, forming the coma, that fuzzy cloud of gas and dust surrounding the nucleus. The coma of 3I Atlas, glowing softly under the bombardment of solar radiation, stretched outward in a tenuous envelope, spanning hundreds of thousands of kilometers, yet remaining so diffuse that it was invisible to most telescopes. But not to XRISM. XRISM, the X-ray Imaging and Spectroscopy mission, is a cutting-edge satellite designed to detect and analyze X-ray emissions from cosmic sources. Launched by the Japan Aerospace Exploration Agency, JAXA, in collaboration with NASA, it carries a state-of-the-art spectrometer capable of resolving X-ray energies with unprecedented precision. This instrument is what allowed scientists to tease apart the faint X-ray signals from 3I Atlas, revealing the chemical composition of its coma with clarity never before achieved for an interstellar object. Now you have two populations of particles in close proximity, high-energy solar wind ions moving at tremendous speeds, and relatively slow-moving neutral atoms from the comet. When a fast-moving solar wind ion collides with a neutral atom, it can steal an electron from that atom in a fraction of a second. This electron capture leaves the solar wind ion in an excited state with the captured electron in a higher energy orbital than it wants to be. Almost immediately, the electron drops down to a more stable, lower energy state, and the excess energy gets released as a photon. The energy of that photon is in the X-ray range, specifically soft X-rays, and the exact energy depends on which atom was involved and which electron transition occurred. The process is a dance of atomic physics, a fleeting interaction that produces a photon carrying the story of its origins. Consider the scale of this interaction. A single solar wind proton, traveling at hundreds of kilometers per second, encounters a neutral oxygen atom from the comet's coma. In a blink of an eye, the proton snatches an electron from the oxygen, becoming a neutral hydrogen atom, while the oxygen atom is ionized. The captured electron, now in an excited state, quickly settles into a lower energy level, releasing a photon with an energy of about 653 electron volts. This photon, now traveling at the speed of light, makes its way through the coma, past the comet nucleus, and out into space. Millions of such interactions occur every second, creating a faint but detectable X-ray glow around the comet. XRISM, positioned in Earth orbit, collects these photons with its sensitive detectors, measuring their energies with exquisite precision. Carbon atoms produce X-rays at certain characteristic energies, nitrogen at others, oxygen at still others. It's like a fingerprint, unique and unmistakable. XRISM's spectrometer split those X-ray photons by energy and counted how many arrived at each energy level. The result is a spectrum, a graph showing intensity versus energy. And in that graph, you see peaks at the energies corresponding to carbon, nitrogen, and oxygen emission lines. These peaks are the whispers from the spectrum, the direct evidence of what elements are present in the coma of 3I Atlas. The data doesn't lie. It speaks in the language of light, and the message is clear. These are the atoms that make up this interstellar wanderer. The ability to detect these X-rays is a testament to the sensitivity of modern instruments. XRISM's detectors are so finely tuned that they can distinguish between photons with energy differences as small as a few electron volts. This resolution is critical because the emission lines for different elements are closely spaced. For example, the carbon K-alpha line, produced when an electron transitions to the innermost shell of a carbon atom, has an energy of about 277 electron volts. The nitrogen K-alpha line is at 392 electron volts, and the oxygen K-alpha line is at 525 electron volts. These slight differences in energy correspond to distinct peaks in the spectrum, allowing scientists to identify the presence of each element unambiguously. And unlike some other observational techniques that require complex modeling to infer composition, X-ray spectroscopy is direct and unambiguous. If you see the carbon line, carbon is there. If you see the nitrogen line, nitrogen is there. It's beautifully straightforward. But it's what those elements mean in context that elevates this from simple chemical detection to something profound. These are biogenic elements, the ones essential for life as we know it. Every carbon atom in your body, every nitrogen atom in the air you breathe, every oxygen atom in the water you drink, they all have a cosmic origin story. They were forged in the cores of stars, scattered across the galaxy by supernovae, and incorporated into new stars, planets, and comets. Now, they're here, glowing in the spectrum of an object that traveled light years to reach us. Observation. The relative intensities of the spectral lines provide insights into the abundance of each element. Carbon's line is the strongest, suggesting it is the most abundant of the three, followed by oxygen and then nitrogen. This aligns with what we know about cometary composition in our solar system, but the ratios are slightly off, hinting at different formation conditions. In solar system comets, the carbon-to-oxygen ratio is typically around 1.2, while in 3I Atlas, it's closer to 1.1.5. This subtle shift suggests that the molecular cloud or protoplanetary disk where 3I Atlas formed had a slightly different chemical inventory than the one that formed our solar system. To understand why this matters, consider the conditions in a molecular cloud. These vast, cold regions of gas and dust are the birthplaces of stars and planets. The temperature in such a cloud can be as low as 10 Kelvin, 263 degrees, allowing complex molecules to form and freeze onto dust grains. The chemical composition of the cloud depends on its history. How many supernovae have enriched it with heavier elements? How much ultraviolet radiation has broken down molecules? And how many generations of stars have cycled through it? The slight differences in the ratios of carbon, nitrogen, and oxygen in 3I Atlas suggest that its birth cloud had a unique chemical signature, distinct from the one that gave rise to our solar system. Now, I'm not suggesting 3I Atlas harbors life or carried life from another star system. There's no evidence for that, and the conditions in and on a comet nucleus are extremely harsh, cold, not conducive to biological processes. But what I am saying is that the chemistry of life, the elemental building blocks, are universal. They're here on Earth, they're in the Sun, they're in interstellar molecular clouds, and they're in Comet 3I Atlas from another star system. Wherever you go in the universe, these elements are present because they were forged in stars and distributed by supernovae and planetary nebulae throughout galaxies. The first stars, formed from primordial hydrogen and helium, seeded the universe with heavier elements through their explosive deaths. Every subsequent generation of stars inherited this enriched material, incorporating it into new planets, new comets, and eventually, new life. The philosophical implication is staggering when you sit with it. We are not separate from the cosmos. We are made of the same stuff as interstellar comets. The atoms in your hand right now, reading this, those atoms were once inside stars. They've traveled through space, condensed into planets and comets, and eventually found their way into you. And 3i Atlas, this visitor from beyond, carries atoms that went through a similar process around a different star, and now they're glowing in X-rays that we detected, completing a circle of observation that connects us across light years and billions of years of cosmic history. The comet is a messenger, a silent envoy bearing tidings from another star system, written in the universal language of chemistry. Unlike local comets, whose formation we can model with reasonable confidence because we understand the solar nebula conditions, 3i Atlas's chemical mix hints at colder birthplaces or different molecular cloud chemistry. The precise ratios of carbon to nitrogen to oxygen, extractable from the intensities of those spectral lines, don't quite match the average we've measured from solar system comets. They're close, well within the range of possibility for natural cometary composition, but shifted enough that it's noticeable. Imagine a recipe with slightly different proportions of ingredients. The outcome might look familiar, but the subtle variations in taste or texture reveal the unique circumstances of its creation. What does that shift tell us? It says that the molecular cloud, or protoplanetary disk, that 3i Atlas formed from had a slightly different chemical inventory than the one that formed our solar system. Maybe that cloud was enriched in nitrogen from a particular generation of stars that exploded nearby. Maybe the temperature gradient in the disk was different, affecting which compounds could condense at which distances from the star. This is the kind of detective work that gets astronomers excited, piecing together a history from indirect clues. We'll never visit the star system where 3i Atlas formed. We don't even know which star that is. But we can read the story written in its atoms. Every element, every isotope, if we could measure them with enough precision, is a clue about the conditions that prevailed there. And the X-ray spectrum, by revealing these elements so clearly through charge exchange, gives us one of the best windows into that story that we've ever had from an interstellar object. Interpretation: the slightly higher nitrogen-to-carbon ratio in 3i Atlas compared to solar system comets could indicate formation in a colder environment. Colder molecular clouds allow more nitrogen to freeze out onto dust grains, incorporating into ices that eventually form comets. This suggests 3i Atlas might have originated in a region farther from its parent star than where most solar system comets formed. Alternatively, the higher nitrogen content could result from the parent star being particularly efficient at producing nitrogen through the CNO cycle, carbon-nitrogen-oxygen cycle, a nuclear fusion process that occurs in the cores of stars more massive than the Sun. There's a researcher whose name keeps coming up in discussions of interstellar visitors, Avi Loeb, who has gained notoriety for suggesting that some of these objects might have artificial origins. He's a serious scientist, but his ideas are controversial and not widely accepted by the astronomical community. I mention him because, in the context of 3i Atlas, some of his followers and others in online spaces have speculated about whether the unusual X-ray properties could indicate something non-natural. The answer, to be absolutely clear, is no. The X-ray emission from 3i Atlas is entirely consistent with charge exchange from cometary outgassing. The spectral lines match laboratory measurements and theoretical predictions for how carbon, nitrogen, and oxygen atoms interact with solar wind ions, There's nothing in the data that requires or even suggests an artificial origin. But here's what's interesting about that speculation from a sociological perspective. It reveals how hungry we are as a species to find evidence of intelligence beyond Earth, how ready we are to leap to that conclusion even when the data doesn't support it. And that hunger isn't wrong. It's beautiful in its own way. It speaks to our deep desire for connection, for knowing we're not alone in the universe. But good science requires discipline. It requires that we follow the data where it leads, rather than where we want it to go. And the data from XRISM leads clearly to natural cometary processes producing X-rays through well-understood physics. No mysteries that can't be explained. No need for exotic hypotheses. What is genuinely mysterious and thrilling, though, is the diversity those natural processes reveal. Even within the framework of comets and asteroids and planets forming around stars, there's so much variation, so many different outcomes possible depending on local conditions, that every new object we study teaches us something. 3i Atlas is teaching us that comets from other star systems can have subtly different chemistry. That charge exchange X-ray emission is detectable and informative. That our models of cometary composition need to account for a wider range of initial conditions. Those lessons are more valuable than any speculation about alien probes because they're real, they're supported by evidence, and they expand our actual understanding of the universe rather than just our imagination. Speculation. If future interstellar objects show similar or even more pronounced chemical variations, it could suggest that planetary system formation is even more diverse than currently believed. This diversity might reflect the wide range of star types, molecular cloud conditions, and planetary system architectures present in the galaxy. For example, some stars are known to be metal-rich, meaning they contain a higher proportion of elements, heavier than hydrogen and helium. Comets formed around such stars might have distinct chemical signatures compared to those formed around metal-poor stars. Over time, as more interstellar objects are observed, these variations could help astronomers map the chemical evolution of the galaxy. Feel that pull? I do. Every time I look at a plot of the XRISM spectrum with those emission lines standing out like peaks on a graph, I feel a connection to something larger. The universe just got a bit more personal, a bit more knowable, because we took the time to look carefully, to build instruments sensitive enough to catch these faint whispers, to analyze the data with rigor and care. This is what I love about science. It's not cold or distant. It's intimate. It's about paying attention to details, about listening to what the cosmos is telling us, and then sharing that understanding with anyone willing to listen. And what the cosmos is telling us through 3i Atlas's X-ray spectrum is that out there, around other stars, in clouds of gas and dust we'll never visit, similar processes to those that formed our solar system are happening, but with variations. Those variations produce diversity, and that diversity is something to celebrate, not fear. Every interstellar visitor that shows up carrying a slightly different chemical signature is expanding our view of what's normal, what's possible, and what the galaxy contains. We're building a catalogue, observation by observation, spectrum by spectrum, of the rich tapestry of planetary system formation. And this X-ray spectrum from 3i Atlas is one of the most detailed threads we've woven into that tapestry so far. But a single observation, no matter how good, is just a starting point. The real power comes from what we do with that information, how we build on it, and where it leads us next. This X-ray first, this breakthrough observation of 3I Atlas, opens doors that go far beyond just this one comet. Think about what we've established here. We've proven that X-ray observations of interstellar objects are feasible and scientifically valuable. We've demonstrated that charge exchange produces detectable signals that carry information about composition and outgassing. We've shown that instruments like XRISM have the sensitivity and spectral resolution to capture meaningful data from faint, transient targets. All of that translates into capabilities we didn't have before. Tools we can now apply to future visitors. Questions we can now ask with confidence that we'll be able to find answers. The implications for future study are immense. Every interstellar object that passes through our solar system from now on is a candidate for X-ray observation. We know what to look for. We know how to interpret the signals. We know roughly what exposure times and pointing strategies work. That knowledge will go into planning future observations, refining techniques, and building even better instruments. The next generation of X-ray telescopes, whatever they are, will be designed with interstellar object studies in mind, informed by what XRISM discovered with 3I Atlas. That's how science progresses, each success building the foundation for the next advance. But the impact goes beyond just interstellar objects. The charge exchange technique that revealed 3I Atlas's composition in X-rays can be applied to solar system comets too. In fact, it has been. But now we have a point of comparison. We can take X-ray spectra from local comets and compare them to the 3I Atlas spectrum, looking for similarities and differences that tell us about the diversity of comet formation conditions. Are all comets in the Kuiper belt similar in composition? Do Oort cloud comets differ? And how do both groups compare to interstellar visitors? These comparative studies will refine our understanding of where and how different populations of small bodies formed, helping to reconstruct the early history of our solar system and others. There's also a timing element that makes this moment particularly significant. 3I Atlas is still moving through the inner solar system. It passed close to the Sun and is now heading outward, making its closest approach to Earth and then continuing toward a Jupiter flyby. Each of these close approaches offers opportunities for different types of observations. Ground-based telescopes are tracking it in visible and infrared light, measuring rotation rates, surface composition, outgassing variability. Radio telescopes might detect molecular emissions, and space-based platforms, if they can spare the time, could take additional X-ray or ultraviolet observations to see how the comet's behavior changes with distance from the Sun. This coordinated multi-wavelength campaign is the ideal way to study any astronomical object. No single wavelength tells the whole story. Visible light shows you the dust and reflected sunlight. Infrared reveals temperature and thermal emission. Radio detects specific molecules. Ultraviolet catches certain atomic transitions. And X-rays expose high-energy processes and charge exchange. Put all those pieces together, and you get a complete picture that none of the individual observations could provide alone. XRISM's X-ray data is one piece of a much larger puzzle, and as researchers combine it with observations from other telescopes, the full story of 3I Atlas will emerge in richer detail than we could achieve from any single dataset. The close approach to Earth is particularly exciting for amateur astronomers and the public. At its brightest, 3I Atlas might be visible in binoculars or small telescopes from dark sky locations. That means you personally could go outside and see this interstellar visitor with your own eyes. Photons that bounced off a comet from another star system entering your pupils and forming an image in your brain. That connection, that personal experience of seeing something astronomical for yourself, is powerful. It transforms abstract science into tangible reality. It's one thing to read about an interstellar comet. It's another thing entirely to see it moving against the background stars, knowing that this faint, fuzzy patch has traveled light years to reach your backyard. As 3i Atlas continues its journey, eventually swinging past Jupiter's orbit, it will begin to fade and recede, moving back out into the darkness of interstellar space. This is a one-time visit. It's not in orbit around the Sun. Its trajectory is hyperbolic, meaning it's going fast enough to escape the solar system's gravity and return to wandering the galaxy. Within a few years, it will be too faint for even professional telescopes to track. It will disappear from our view, continuing its journey to wherever gravity and momentum take it next. Maybe in millions of years, it will encounter another star system. And if beings there have developed astronomy, they'll get to study it the way we're studying it now. Or maybe it will drift through the void for billions of years, a frozen relic carrying the signature of its birth star, untouched and unobserved. That sense of fleeting opportunity adds urgency to the observations. There's a narrow window when an interstellar object is close enough and bright enough to study in detail, and that window is closing. Every observation that doesn't happen now is a lost opportunity. Data we'll never be able to collect from this particular visitor. That's why teams like JAXA's XRISM group act quickly when opportunities arise. They understand that in astronomy, timing is everything, and second chances are rare. The JAXA team, in their public communications about the observation, emphasized its revolutionary nature. This is not hyperbole. It is genuinely the first time an interstellar object has been observed in X-rays with enough sensitivity and spectral resolution to extract detailed compositional information. That's a revolution in technique, in capability, and in understanding. The word revolutionary gets thrown around a lot in science journalism, often applied to incremental advances that are interesting but not paradigm-shifting. This is different. This is opening a new observational window onto a class of objects that we barely understand because they're so rare and fleeting. That's genuinely revolutionary. And importantly, there's no threat. Let me be absolutely clear about that, because whenever interstellar objects make headlines, there's a subset of people who worry about impacts or dangers. 3i Atlas poses no threat to Earth. Its trajectory is well understood, tracked by multiple observatories, and there is zero chance of collision. It's going to pass by at a safe distance, close enough for good observations, but far enough that there's no risk whatsoever. This is pure discovery, pure science, with no danger or downside, just the joy of learning something new about the universe. But that glow from the X-ray observation, that spectral signature captured by XRISM, lingers in the minds of researchers and enthusiasts alike. It's not just data. It's a reminder that we live in a time when we can actually study objects from other star systems. For all of human history until recently, interstellar space was unreachable and unknowable except through theory. We could study our own solar system. We could observe distant stars and galaxies. But the space between stars, the objects drifting through that void, those were beyond our reach. Now they come to us, and when they do, we have the tools to study them. That shift from theoretical to empirical, from guessing to knowing, is profound. It also raises the question, what else hides in X-ray silence? How many other phenomena in the universe are invisible in the wavelengths we commonly observe, but glowing brightly in X-rays or other exotic parts of the spectrum? Every time we develop a new observational capability, we discover things we didn't expect. Radio astronomy revealed pulsars and quasars. Infrared showed us dust-obscured galaxies and young stellar objects. Gamma-ray observations found bursts from distant cosmic catastrophes. Each new wavelength opened a new chapter in our understanding. X-ray observations of interstellar objects might seem like a small niche, but they're part of that larger pattern of expanding what we can see and therefore what we can know. Looking ahead, there are missions in development and being proposed that will have even better X-ray capabilities than XRISM. There are plans for larger collecting areas, better energy resolution, faster detectors that can track variability on short time scales. Each improvement will make observations like the one XRISM performed on 3i Atlas easier, more detailed, and more informative. Eventually, X-ray observation might become routine for interstellar visitors rather than a special achievement. And when that happens, when we have X-ray spectra from dozens or hundreds of interstellar objects, we'll be able to do statistical studies that reveal patterns and trends invisible in small samples. Imagine a future where we can say with confidence that interstellar comets from metal-rich stars have different compositions than those from metal-poor stars, where we can trace the chemical evolution of the galaxy by studying the visitors that wander into our neighborhood. That future is being built right now, one observation at a time, starting with breakthroughs like XRISM's X-ray image of 3i Atlas. The bigger shadow this observation casts is one of possibility, of potential, of doors opening onto new areas of research that will keep astronomers busy for decades. And all of it stems from that decision to point an X-ray telescope at an interstellar comet and see what happens. Simple in concept, profound in impact. That's often how the best science works. But for all these implications and future possibilities to matter, we need to connect them back to something personal, something human, something that reminds us why we care about distant comets and invisible light in the first place. From Japan's mission control room, where engineers monitored satellite telemetry and scientists analyzed incoming data, to your screen right now, wherever you are in the world, this X-ray glow connects us all to stars unknown. It reminds us that we're part of something vastly larger than our individual lives, our cities, our planet. The cosmos isn't something separate, something out there that has nothing to do with us. We're embedded in it, made from it, connected to every star and galaxy by threads of physics and chemistry that stretch across space and time. When I think about the people who made this observation possible, I'm struck by their dedication. The engineers who designed XRISM, spending years solving technical problems, ensuring every component would work in the harsh environment of space. The scientists who wrote the proposals, making the case that observing an interstellar object in X-rays was worth the investment of precious telescope time. The data analysts who processed raw signals into meaningful images and spectra, applying corrections and calibrations, ensuring every photon was counted accurately. The theorists who built models to interpret the observations, connecting the dots between atomic physics, solar wind dynamics, and cometary outgassing. Every one of these people contributed to this moment of discovery, and most of them will never be famous, never receive public recognition, but their work matters immensely. Science is a collective endeavor. It's built on the contributions of thousands of people, each playing their part, each adding their piece to the puzzle. The XRISM observation of 3I Atlas stands on foundations laid by decades of X-ray astronomy development, by space missions that came before and learned hard lessons, by theoretical work that predicted what we might see if we looked. No single person or team could have done this alone. It took a community, a global community of researchers and engineers and technicians, all working toward the common goal of understanding the universe better, and now their work is bearing fruit in the form of this historic image and the scientific insights it provides. But it's not just for scientists. This discovery belongs to all of us. Every person who ever looked up at the night sky and wondered. Every child who asked why stars shine. Every adult who felt a moment of awe at the vastness of space. You're part of this story too. Science is humanity's collective effort to understand reality. And when we succeed, when we make a discovery or answer a question, the knowledge becomes part of our shared heritage. You don't need a PhD to appreciate what it means that we've seen an interstellar visitor in X-rays for the first time. You just need curiosity and wonder. And I believe those are universal human traits. The cosmos shares secrets when we look right. And by looking right, I mean with the right tools, at the right times, with the right questions in mind. For millennia, humans looked at comets and saw omens or signs from gods. We didn't know they were icy bodies from the outer solar system. We didn't understand their orbits or their composition, but we looked and we wondered, and eventually we developed the tools and methods to answer those questions. Now, we're in a new phase where we can study not just local comets, but visitors from other star systems. And we're finding that the same approach works. Observe carefully, measure precisely, analyze thoroughly, and let the data guide your understanding. 3I Atlas reminds us that the universe is generous with its secrets if we're willing to do the work to uncover them. It didn't hide its X-ray glow out of malice or mystery in the mystical sense. The X-rays were always there, produced by natural processes, waiting for us to build instruments sensitive enough to detect them. And when we did, when XRISM turned its gaze on this interstellar visitor, the secrets revealed themselves. That pattern has played out over and over in the history of science. Nature doesn't lie or deceive, it simply is. And our job is to observe and interpret accurately. There's a particular kind of joy in that, a satisfaction that comes from knowing we're getting closer to truth. Not truth in an absolute philosophical sense, because science is always provisional, always ready to update based on new evidence, but truth in the sense of accurate, testable, predictive understanding of how things work. The X-ray spectrum from 3I Atlas is truth in that sense. It's a real signal from a real object interpreted through established physics, checked and verified by multiple experts. It tells us something true about the universe. And that truth is now part of human knowledge forever. Soon, very soon, depending on when you are watching this, you'll have a chance to participate in this story personally. Grab binoculars if you have them, or find a local astronomy club that might have telescopes set up for public viewing. Go to a dark sky location if you can, away from city lights, and look for 3-eye Atlas. It won't be the most spectacular thing you've ever seen. It'll be a faint, fuzzy patch, maybe moving slowly against the background stars over the course of several nights. But knowing what it is, knowing that this faint, fuzzy patch has traveled across light years from another star system, knowing that professional telescopes have captured its X-ray glow and decoded its chemical composition, that knowledge transforms the observation into something profound. You're not just seeing a comet. You're seeing a messenger from another part of the galaxy, carrying information about places and times we can only imagine. You're witnessing a piece of another world, another star system, that has come within reach of your eyes and your binoculars. That's a privilege our ancestors couldn't have dreamed of. They saw comets, but had no idea some were interstellar. We have that knowledge, and it enriches the experience immeasurably. And here's what makes me smile every time I think about it. Somewhere out there, light years away, maybe there's a star system around which 3-eye Atlas formed. Maybe planets orbited that star. Maybe on one of those planets, beings like us, utterly different perhaps, looked up at their sky and wondered about the universe. Maybe they never knew that one small icy body from their system would eventually be ejected and wander the galaxy. Or maybe they did know. Maybe they watched it leave and wondered where it would go, whether anyone would ever see it again. We're answering that question now. Yes, someone saw it. We did. We studied it. We learned from it. And in doing so, we connected across the galaxy, not through messages or technology, but through the simple act of observing a shared cosmic object. You're part of this story now, not passively, not just as someone reading or watching, but actively. Your engagement, your curiosity, your willingness to spend time learning about this observation, that matters. It's part of what keeps science alive and vibrant. When the public cares about discoveries, when people get excited about learning new things about the universe, that energy feeds back into the scientific community. It justifies funding for missions like XRISM. It inspires the next generation of researchers who see that people care about this work. It creates a culture where understanding the cosmos is valued, and that culture is what enables all the technical achievements we've been discussing. So as you think about 3-eye Atlas glowing in X-rays, captured by a Japanese satellite, remember that you're part of the chain that makes such discoveries possible and meaningful. From the scientists, to the engineers, to the public who supports and celebrates their work, we're all connected in this grand endeavor to understand the universe we live in. And every once in a while, that endeavor gifts us with something special, something that cuts through the noise and reminds us why we look up, why we wonder, why we explore. This X-ray image is one of those gifts, and I'm grateful to share it with you. But every story, no matter how cosmic in scope, needs a conclusion, a moment to reflect on what we've learned and where we go from here. We've unveiled the X-ray stranger together, you and I, tracing its journey from detection by JAXA's XRISM satellite through the science that explains its glow to the implications that extend far beyond this single observation. We've explored how charge exchange creates X-ray emission, how spectroscopy reveals composition, how this interstellar visitor differs subtly from the comets we're familiar with, and why those differences matter for understanding the diversity of planetary systems throughout our galaxy. This wasn't just about a comet. It was about what that comet represents, a message from elsewhere, written in atoms and light. If this blew your mind even a fraction as much as it did mine, I need you to do something for me right now. Hit that like button. Seriously, click it. That simple action tells me this content resonated with you, and it tells the algorithm that this kind of deep, thoughtful science content is what people want to see. Every like is a vote for more content like this, for going beyond surface-level facts and really diving into the wonder and implications of what we're discovering about the universe. So thank you if you've already liked, and if you haven't, pause right here and do it now. I'll wait. Now here's where I really want to hear from you. Drop a comment below with your wildest theory about 3I Atlas or interstellar objects in general. Where do you think this comet came from? What kind of star system do you imagine formed it? Do you think we'll ever identify its origin, trace its trajectory back to a specific star? Or what do you think the next interstellar visitor will reveal? I read every comment, and I love seeing your ideas, your questions, your perspectives. The conversation doesn't end with the video. It continues in the comments, and some of the most interesting discussions happen there. So, jump in and share your thoughts. If you're not already subscribed to this channel, what are you waiting for? We're going to be following 3I Atlas through its flyby of Jupiter, and I'll be covering the latest observations and discoveries as they come in. There's going to be more data, more insights, maybe even more surprises as other telescopes contribute their observations. You don't want to miss those updates. Hit the subscribe button and make sure you've turned on notifications so you're alerted when new content drops. We're in the golden age of astronomy, with new discoveries happening constantly, and I'm committed to bringing you the most interesting, most thought-provoking stories as they unfold. There's a question I want you to think about, and maybe answer in the comments. Where will you be watching 3I Atlas pass? Are you in a location with dark skies where you might actually see it? Or are you stuck in a city where light pollution hides all but the brightest objects? If you can get out to observe it, will you? Is this something you'd drive a few hours for? To stand under dark skies and witness an interstellar visitor with your own eyes? I'm curious about your relationship with the night sky, how accessible it is for you, and whether discoveries like this motivate you to seek out observing opportunities. Share your story below. Are you a seasoned amateur astronomer with a backyard telescope, or someone who hasn't looked at the stars in years but feels inspired by this? Both perspectives are valid and interesting. The beauty of a discovery like this is that it works on multiple levels. For professional astronomers, it's a technical achievement, a source of data that will fuel papers and PhD theses, that will refine models and inspire new observational campaigns. For educators, it's a teaching opportunity, a way to explain spectroscopy, solar wind, planetary system formation, all grounded in a real current event. For space enthusiasts, it's another piece of the puzzle about interstellar objects, adding to the story started by Oumuamua and Borisov. And for the general public, for anyone who's ever felt wonder at the night sky, it's a reminder that we live in an amazing universe full of surprises, that science is actively discovering new things, and that we're all invited to be part of the journey. That's what I try to create with this content, a space where all those levels can coexist, where I can go deep enough to satisfy people who really want to understand the details